All right. Good afternoon, everyone, or good morning or good evening, depending on where you're joining us from. I'd like to welcome you all to our webinar today. My name is Meta Polywall with the Orange County Water District. And today's webinar is Advancing PFAS Management, Progress, Lessons, and Tools for Retail Agencies. Today's webinar will provide an overview of OCWD's PFAS program, including current progress, key operational lessons learned, and the coordinated approach being taken with our retail water agencies. Our speakers will highlight countywide well restoration efforts to date and will provide a glimpse into a new PFAS dashboard and how it supports timely data access and informed decision-making by our staff. And before we get started, I do want to mention that we are in webinar mode to reduce any background noise. The webinar is being recorded and will be published on OCWD's YouTube channels. We do encourage you to ask your questions today, so please use that Q&A box located at the bottom of your screen to submit questions on today's topic. And you can always email us after as well, so please don't hesitate to email info@ocwd.com with any follow-up questions. We're going to do our best to get to as many questions live today, so please do use that Q&A box, and we'll take questions at the end of the presentation. Without further ado, I'd like to introduce our speakers today. Ryan Boley is the Director of Engineering at the Orange County Water District, where he oversees district projects from initial stages of concept and feasibility to the final stages of design, construction, and commissioning. Since OCWD began large-scale pilot testing in 2019, Ryan has coordinated with various stakeholders, including consultants, contractors, state regulators, and groundwater retail agencies to further the district's efforts to develop cost-effective PFAS treatment processes. To date, Ryan has directed various stages of planning, design, construction, and commissioning of PFAS treatment systems at multiple sites for several retail agencies in Orange County. Ryan has extensive expertise in civil and groundwater recharge-related projects, spanning 25 years of construction and project management. Andrew Huang is a senior laboratory analyst data scientist at the Orange County Water District's Research and Development Department, where he helps implement data-driven initiatives to support water reuse operations and research. With several years of experience working in the lab and across digital environments, Andrew bridges disciplines by combining hands-on scientific research with applied statistics and real-time data systems. His work integrates Internet of Things, cloud computing, and interactive dashboards to transform complex data sets into actionable insights for operators, engineers, and decision makers. With that, I'd love to turn it over to Ryan to get us started.
Oh, thank you very much, Meta. I appreciate that kind introduction. I am going to share my screen. Let's see. There we go. All right, and hopefully that is showing up for you. Am I good, Meta?
Yep.
All right, perfect. Great. Well, thank you all for joining us today. As Meta said, my name is Ryan Boulay. I'm the Director of Engineering with Orange County Water District. I've had the pleasure of working at the district for over 10 years and the fortune of being involved with PFAS projects through piloting and, as she mentioned, commissioning since the start of our program in 2019. It's been quite a ride and a lot of lessons learned, and I'm hoping that I can share some of those with you today. First off, though, I want to start with a little bit of background on OCWD. For those of you that don't know, Orange County Water District was formed in 1933 through an act of the state legislature. We have, through sound groundwater management principles, we've been able to provide 85% of the drinking water supply to 19 cities and retail water districts in North and Central Orange County. That's equal to about 2.5 million people served. We do have a 10-member board that is comprised of various elected and appointed members throughout those 19 cities and retail water districts. And very importantly, we protect the rights to the Santa Ana River water. And what does that mean? Well, here's an overview map. The green shows the limits of Orange County Water District service area. And up to the top left, or excuse me, top right, let me get a laser pointer here. Up in the top right, you can see Prado Dam and Prado Basin here. Water flows from the San Bernardino, San Gabriel Mountains all the way down Santa Ana River. As it flows down the river, once it gets to about the Anaheim area, it is uh, detoured off the river into OCWD's groundwater basins. Here's a photo of one of our larger basins here. We take that water and recharge that into the ground. That's provided or given us the ability to provide 85% of the drinking water to Orange County. One of the challenges with that is PFAS has come down the river with that water. And so that's why we're here today to talk about what we're doing to fix that. But a little bit more detail here. Circled is where the majority of OCWD's recharge basins are. And looking at this next slide, you can see all of these orange areas are the recharge basins, including the river itself. It's a nice sandy substrate, and the water goes right into the aquifer very easily. We have several off-river basins that are either piped or water is pumped to those all over Orange and Anaheim and this has been in operation for about 50 years now, and it works great for storing water and unfortunately getting PFAS into the aquifer. Um, so PFAS impacts at OCWD. We've identified 100 wells so far that need treatment, and I say so far because unfortunately water does move underground carrying PFAS with it. 15 retailers have been impacted so far, again. With what we've identified, we're estimating about a $1.8 billion total cost, and that's a life cycle cost over 30 years of construction, O&M, replacement imported water when some of those wells are turned off because of legal requirements, etc. This map here shows all of the wells that are impacted. So these green dots and blue dots show various wells that we've detected PFAS over the newly adopted MCL. So as you can see, this is where all of our recharge basins are. It has spread out through the basin all the way across the basin. So unfortunately, some of these others may hit at some point. We'll just have to wait and see and deal with those as they come. So I just wanted to share a quick timeline of OCWD and PFAS. Back in 2018, the Department of Drinking Water, DDW, established a response level for PFOA and PFAS. At that point, OCWD, through its just standard testing and maintaining water quality, identified 10 of the retailers' wells that were impacted by this new RL. That was a total of 62 wells. And so that was what we called round one of our program. We started a PFAS pilot study testing multiple media with multiple retailers' water just to find out which media would be best. PFAS treatment systems planning study. That was kind of a preliminary engineering study looking at all of these impacted wells, citing various types of media treatment, seeing which would work best for space and water flow rates and just trying to identify quickly what would be the best course of action. We established a PFAS policy with all of the water retailers, what we also call producers. We started that policy back in 2019, and we agreed that we were going to take the lead on treating any well that was showing PFAS levels over 80% of the established RL or response level. Fast forward to 2020, OCWD issued its first RFP for vessels. We ended up purchasing 100 IX vessel systems, and that each system is 2 vessels, so a total of 200 treatment vessels. We selected 2 vendors with that RFP, and they were able to supply the vessels we needed for round 1 and some of the round 2 sites. OCWD also issued an RFP for on-call consulting. We selected 6 consultants on an on-call basis, so we were able to react quickly as new wells started to show up. We could write work orders quickly, have design started quickly, and hopefully get construction started as soon as possible. So in 2020, design and construction started for the first few well sites. In 2021, Jacobs, working with OCWD, published their PFAS treatment testing study final report. And that was a really great document that details OCWD's pilot testing results. And we'll talk a little bit more about that pilot testing here in just a minute. OCWD also purchased our first IX media based on our pilot results, and the first PFAS treatment sites were operational in 2021. So a little over a year, year and a half from initial design to construction. So we really fast-tracked early on. And then fast forward to 2024, a lot of the same happened from 21 to 24, just more projects, more construction. But in 2024, the EPA released its final PFAS drinking water regulation of 4 parts per trillion for PFOA and PFAS. And with that, OCWD identified 44 additional wells above that 4 parts per trillion. Now, that was in 2024. We've still seen a few more wells creeping in. So where are we today? This next slide shows a graphic of our current status. So we have 53 wells operational. So of the 106 that are currently identified, we're halfway there, which is great. 16 are in construction with 26 in design. That number is going to change very soon. We have several projects coming out to bid, so it's going to essentially flip-flop to 26 in construction and 16 in design. And then we have 11 in planning. And what planning means is that we're waiting for some results to show where PFAS is above the MCL, or the owners of the wells may want to re-drill the well. And so we haven't identified the location yet. And so we're just waiting until that's done to actually implement treatment. So developing solutions. It all started with our PFAS policy. OCWD manages a groundwater basin for all of these 19 cities and retail water districts. They all have the rights. We're a non-adjudicated basin, meaning that nobody owns the water underneath. It's all the rights of OCWD, and the producers are able to pump that water. Given that, we approached an all-for-one, one-for-all management approach, treating all of the retailers equally. OCWD agreed to finance, design, and construct these treatment systems for the impacted wells. The retailer would maintain ownership and operation of the well and the treatment, and all of the O&M costs over a 30-year life cycle would be shared 50-50 between OCWD and the retailer. PFAS concentrations had to be greater than the applicable response level or maximum contaminant level for the well to apply. And to date, we have 15 agreements with 15 of the 19 cities and retail water districts. So most everybody is part of the agreement. We have 4 that haven't been impacted yet, so they're not part of the agreement yet. But again, they may be in the future. So the second part, and really the key source of momentum in PFAS removal for us, has been our research and development. So OCWD has a fantastic research and development team that's dedicated to basically studying how to keep water better, how to treat water better, make it cleaner, make it safer, make it more cost effective for everybody. And again, without them, without our research and development department, we would probably still be at the starting blocks with PFAS removal. So they've helped us identify technologies that we can use for reverse osmosis or for PFAS removal. The first is reverse osmosis. We're currently using that with our GWRS system. It's very effective. It removes essentially everything from water, including PFAS. However, it's energy intensive, has a very large footprint and really expensive, the highest cost of all of the identified technologies. The next technology that we identified was ion exchange. It has a higher capacity per system than the next one I'll talk about, a smaller footprint, lower capital cost, and but it does have a higher media purchase cost. The next is granular activated carbon. Again, compared to ion exchange, it has a lower capacity per system, a much larger footprint because of that lower capacity per system. Higher capital cost, again, related to more vessels needed to treat the same amount of water. However, the media is much less expensive. So there's trade-offs with both technologies. Ultimately, reverse osmosis was too expensive, so we focused on ion exchange and granular activated carbon for all of our treatment sites throughout Orange County. PFAS research. So the pilot testing I had spoken about earlier. This right here, you can see the photo on the left shows our initial pilot skid back in 2019. You can see the multiple columns. We were piloting 4 different types of granular activated carbon and 6 different types of ion exchange resins or alternative adsorbents, novel adsorbents are also called. We ran those in a pretty much a full scale type pilot that ran to failure. So this system ran for over a year, and we were able to monitor the PFAS levels as it was running and really get a good feel for which media was performing best, which broke through first, which lasted longest, and ultimately helped to determine which one was going to be most cost effective for OCWD and the retailers. So from there, we started implementing treatment. This is the ion exchange media that we're ultimately using. It's a Amberlite PSR2 Plus. On the left, you can see a photo of it. It's kind of a light, creamy white tan color. On the right over here, you can see the size of the media compared to a penny. I apologize, I didn't have a millimeter ruler, so I had to go with a penny, but it's a very small resin. Very small pore spaces between the individual resin grains. What that means is that the ion exchange system that's preferred for most sites, it ultimately requires prefiltration. Now, the prefiltration removes anything in the water upstream of the IX treatment larger than 5 microns. And that you can use cartridge filters or bag filters, but you really have to remove that larger than 5 micron material, or else it will clog those pores in between the little individual media grains, and your media bed will stop working much sooner. So for our typical ion exchange layouts for 99% of our sites, we're using a 1220 dual vessel system. That means 12-foot diameter. It can hold up to 20,000 pounds of media. It's a 16-foot height overall with a 1,600 gallon per minute flow rate using 424 cubic feet of this media. And that provides a 2-minute empty bed contact time per vessel, meaning that the water is 2 minutes of contact with the media to remove PFAS. Lead lag configuration, what does that mean? I'll use this one over here. A lead lag means that the water will come in and go through one vessel out the bottom, and then go up through the second vessel, out the bottom, and then off to distribution. So it's a redundant system, meaning that it goes through 2 different sets of resin beds to make sure that everything is treated and the water is in fact treated to completely remove the PFAS. PSR2 Plus from, well, Evoqua is our supplier, but it's a Purolite, or excuse me, a Amberlite material. The bag filters, that's one method that we can use to remove that 5 micron plus particles out of the water. You can see this photo here. These bag filters are oriented in a vertical configuration. They're accessed from the top, so they require quite a bit of scaffolding or ladders or other things in order to maintain these in the long run. which means they up a little bit more, uh, take up a little bit more of a footprint. So they're larger and more spread out. They're a little bit more difficult to access because of their height, and there is just more hardware involved. The benefits to these, their bag filters are a lower unit consumable cost. The bag filters themselves are less expensive, and there's less of them in these cartridge canister or bag filter canisters. So cartridge filters, these are in a horizontal plane here. They're a smaller footprint. They're much easier to access because they're in that horizontal plane and there is less hardware. Of course, the trade-off is they have a higher unit cost per consumable. And if you look at each of these canisters, there's 3 here. There are hundreds of these individual filters per vessel. So there's a lot to change out. It's labor intensive, and the cartridges themselves can be a little bit more expensive as well. So moving on to granular activated carbon, which is the other treatment that we're using. One of the benefits for GAC is that there's no pre-filtration required. Those pre-filters we just talked about, you don't need those with GAC. However, it does require a backwash. And what that means is periodically those larger than 5 micron particles will start to clog the bed. While you run water in reverse through the systems, you can either recover that water, which is what's happening in this tank over here on this site, or if your jurisdiction allows, you can directly dispose it to sewer or storm drain. The GAC vessels themselves, we can use vessels that are identical to the IX vessels, or we can use what's called a 1240 system. These are 1240s. They're 26 feet tall, so 10 feet taller than the ones we saw in the other photo. Still 12-foot diameter. However, these have a 1,000 gallon per minute flow rate. These shorter ones that we saw for IX, if we were to use GAC in those same vessels, it would only be 500 gallons per minute, so about 1/3, meaning you would need about 3 times the number of vessels and therefore more real estate. So that's why we've chosen IX for most of our sites. This actually, the reason we're using granular activated carbon at this particular site is because of co-contaminants, volatile organic compounds, or other organics, basically carbon compounds that are not compatible with the IX media. These require a 10-minute empty bed contact time per vessel, and that's part of what makes them so much larger and makes you require more vessels overall. And of course, the media that we tested out best for our particular usage was the Calgon F400, and that's what we're using at this site. So now moving into some of our issues and lessons learned, there is going to be head loss and impacts to your system if you're implementing PFAS treatment. You can't get around that. The pre-filters will clog up over time, and that will increase head loss. The media will start to degrade, clog up, that will increase head loss. So up front, looking at it from a design point of view, you may either decide that it's okay to lose flow, or you may decide you have to upgrade your pump and drive and power system in order to make that work. Footing designs. Installing these vessels can be pretty tricky. There's a lot of parts that have to assemble, and some of them are very rigid. So 2 options: you can cast in place these anchor bolts that are shown here, which is, you cast your foundation, the anchor bolts are already installed. But if you have 4 of these bolts times 8 legs, that's 32 bolts. All of the holes have to line up. That can be difficult, or it can be a risk. So this contractor here elected to install post-installed anchors, and basically they blocked out a hole underneath the leg of the vessel. They set the vessel on some steel plates, hung the anchor bolts from the vessel, and backfilled this with concrete later. That takes away all the guesswork, and it allows for maximum adjustability during construction. IX feed and return pipe placement. I've had some sites where the piping was designed underneath the slab, and other sites where the piping was not. We did find that there was a significant schedule impact to the pipe being placed under the slab, because that pipe has to be installed before the slab can be built. So it sometimes space doesn't allow anything different, but if you can avoid it and you have a schedule consideration, avoid placing piping under the vessel pads. Maintenance flushing. If the system is not going to be run every day, you will need to do some maintenance flushing, and that's just to keep the media fresh, prevent bacteria growth. Um, Convenient drain locations will be a lifesaver for you. You can see here in the photo, they placed a drain inlet directly below the discharge, and this is just a maintenance discharge here from the vessel systems. Makes it really easy to perform that maintenance flushing and not have to have a bunch of hoses that you direct water over to a drain anywhere. SCADA controls. So SCADA, for those of you who aren't familiar with SCADA, SCADA is basically the computer system that controls all the physical stuff at a site. There's an existing system most likely that controls your well, and it controls the pump. It controls all of the power going in and out of the site and all of the devices that keep everything running. PFAS treatment will add to that SCADA. There's a few inputs and outputs, not many, but there are some. We found several sites where the existing SCADA controls were out of date. It's just like a computer, the software is not supported anymore, or the computer's not supported anymore. So we had to replace PLCs or upgrade equipment. So that's something that you'll have to look at. There could be more costs than you're anticipating there. Non-chlorinated water for flushing. That maintenance flushing I was talking about and flushing at startup. IX media is incompatible with chlorine. The chlorine can turn the media into goo, melt it more or less. So you don't want to use any chlorine in the water in the media. And then sanding in wells. Sanding is a term that we use for any kind of sand or material down underground that makes it through the well screen and up into the water. If you have sanding at a well site, it will prematurely fill and age your cartridge or bag filters. So you really should deal with the sanding somehow. In this photo, you can see this vertical blue device here. That's a sand separator. So the water comes in and it circles around and it comes out and it tries to flush as much of that sand out of the water prior to going into the cartridge filters that are shown here. So co-contaminants clogging and what we call skimming. There are we've had several sites with iron and manganese that have led to premature clogging of the top few inches of our media beds. And again, on the left, you can see this nice clean resin. On the right is the resin after it's been subjected to water with levels of iron and manganese. And you can see it's kind of black and brown, and there are shooting water in it to break it up, but there was kind of a gooey, sticky mess on top of the media bed. And that was preventing water from flowing through the media and ultimately, rendering the treatment ineffective. So that's another consideration. Look at your water chemistry prior to design and make sure that you're treating any of these co-contaminants that will cause clogging as well. So now I'm just going to go into a few photos. This was our GAC system once it was finished, nice paved roads, but it shows our vessel systems here with our backwash tank. This here is our largest PFAS treatment system to date. There are 11 systems, 22 vessels. This is Yorba Linda Water District, their central plant, they call it, because they took all of their wells and ran all of that water to one centralized plant right behind their office, which is just off screen in the photo here. That makes it really convenient for maintenance and service. So that's one alternative if your wells are close together. This is another smaller centralized plant in Tustin. 4 systems here. You can see this one has bag filters off to the side, but they're slightly recessed in a structural pit, which actually does make the maintenance much easier, and some of that additional piping is hidden or underground, so it saves a little bit of usable real estate up top. This is the configuration that we have for again, probably 99% of our treatment sites. Just vessel systems stacked up to make 1,600 gallons per minute per system, to match the flow rate of the well. You can see here this one has a sand separator off to the side. This one must have a sanding issue in the well itself. Here's another one. Again, just a standard two systems next to each other. This particular site was really nice. It was a brand new well, brand new treatment vessels, and a brand new chlorine building with on-site chlorine generation. Now, maybe you have a site with visual restrictions or visual concerns. The next couple photos show some alternatives. These vessels were placed into a recessed pit. So the floor of this pit's about 10 feet below existing ground, making the top of these 16-foot vessels right about even with the block wall behind it. So it's very easy on the eyes from the front of the site and hard to see. And then here's another very similar recessed pit, similar situation. You can see it's surrounded by residential, and they just wanted to be nice neighbors and place these vessels in a recessed pit. So that's all I have for the implementation, and I'm going to hand it over to Andrew for tracking. Get this shared. There we go.
All right. Thanks, Ryan. So yeah, my name is Andrew Huang. I am a senior laboratory analyst and data scientist here at OCWD's R&D department. And while Ryan told you about how we're physically removing PFAS, I'll be telling you about the other challenge in our new PFAS treatment program, which is the data management. So just over the course of a few years, PFAS went from being an unregulated compound to being a major part of our operations. So I'll show you how we keep all of our PFAS monitoring data organized and actionable despite the influx of all this new data. So first off, to understand why the data poses a challenge, I need to just give a bit more background about how the treatment facilities are operated. As Ryan mentioned previously, we use ion exchange adsorbent media to treat the PFAS at the majority of our treatment facilities. But unfortunately, the adsorbent media has a finite life before it's exhausted of its adsorbent capacity, meaning we need to anticipate and change it before it's reached that point. So as a result, we need to closely monitor PFAS concentration of water at multiple stages in the treatment train by taking samples and testing it with EPA method 533. So one important thing to note is that while we do the sampling and PFAS testing for the treatment facilities, the actual operations are handled by the cities and retail water agencies themselves. And we work closely with them to advise them when to change out the media. So on the right side of your screen, you'll see a treatment facility with two trains, with each train consisting of two vessels. So treatment vessels are organized in a lead lag configuration where untreated water goes through the two treatment vessels in series, called the lead and lag respectively. So highlighted in green, that's the lead vessel, which is where the water first enters. And then the effluent from that goes into the lag in purple. So the lead lag setup allows us to use the lead vessel as an indicator because we can measure what's coming out of the lead before it goes into the lead vessel. And once the lead vessel is exhausted of its adsorbent capacity, we change the ion exchange media. So this is to give you an idea of what our PFAS monitoring actually looks like operationally. Currently, we have 27 treatment plants online, but that final number will likely be around 68. For each treatment facility, we're required to do monthly sampling of the lead vessel and combined effluent. But additionally, we also have to do quarterly sampling of all the points in the treatment train, which includes influent, lead, lag, and the combined effluent. So samples are brought to our lab, where they're tested for 25 different PFAS analytes using EPA method 533. And I think we probably have the highest volume of samples analyzed for PFAS of any public agency in the country. So we're currently analyzing about 5,000 PFAS samples a year. And we were also the first public agency lab to be accredited for testing PFAS in drinking water. So with the number of treatment facilities, multiple treatment trains per facility, monthly and quarterly sampling, and number of analytes measured, we're constantly generating a huge amount of PFAS data. And here's the data challenge, just to put the scale into perspective a bit. With 27 treatment plants currently online, again, with total 68 planned, monthly and quarterly sampling requirements, 25 PFAS analytes tested as a part of Method 533, and up to 22 treatment vessels per facility, we're generating approximately 100,000 individual PFAS measurements annually. And that number is only going to increase even further once we have all the treatment facilities online. So that begs the question, how do we manage all of this data and make sure it's actually usable? Well, one of the ways is through a PFAS treatment facilities dashboard. So this is an in-house developed dashboard created in R using the Shiny framework and deployed on our internal servers. It runs from your web browser, so you can bookmark it and access it without launching any additional programs. The application is able to pull data automatically from various sources, including our laboratory database and various uploaded CSV files. And it also just automatically refreshes once a day. It was also created and deployed using free open source tools. This wasn't a requirement or anything, but it's a nice bonus. One of the main priorities for the tool was to create a quicker workflow and to give both an at-a-glance high-level overview, but also give the ability to drill down deeper into the data if necessary. Another goal was a user-friendly interface. We wanted to make sure somebody who had never seen the tool before could start clicking around intuitively without actually being trained on it. And lastly, it also serves to sort of democratize the data by giving access to more stakeholders. Whereas before you might have a couple people with a running spreadsheet where they have to constantly query the data, update the spreadsheet and send it out, you now have a dashboard that's accessible to all stakeholders who can explore the data themselves. So now I'm just going to give a quick overview of what the dashboard looks like and some of its current capabilities. A quick disclaimer is that all the city and well names were anonymized for this presentation. But we start out here on the home page of the dashboard. So on the left side, there's a map module with all the treatment facilities colored by PFAS breakthrough. So green means there's no breakthrough, orange means there's breakthrough in the lead vessel, and red means there's breakthrough in the lag vessel. Again, this goes back to the idea that we should have quick at-a-glance information. So here we can immediately see what sites have experienced initial breakthrough and monitor them accordingly. So if you click on one of those sites, we can see more detailed info about it, including which city or retail agency it belongs to, the number of treatment trains, and when it was last sampled. And also on the right side of the screen, it'll show the latest PFAS measurements for that particular site, along with when each vessel was last changed out. So still on the home page, but scrolling down a bit, we can see an overview of the influent and effluent going in and coming out of these treatment facilities. That top chart is effluent and the bottom chart is influent. As you can see, there's varying levels of PFAS going into each site, but it's all being removed to extremely low or non-detect levels. We specifically focus on PFAS analytes with the regulatory limits, but the dashboard is capable of viewing them all. In this next tab is the operating parameters for each site. So this page just serves as a quick reference to see basic facts about each treatment facility, including the city, the well name, number of treatment vessels, when it was put into service, and the amount of media per vessel. But this table is mostly static. It just helps keep all of our treatment facility info in one place so you don't have to consult another document. This next page shows the vessel changeout dates for each treatment vessel. This includes info like if it's currently serving as a lead or a lag, when it was put into that position, how many days have elapsed since then, and the last measured PFAS values from that vessel's effluent. So you can filter and sort each column. So for example, if you were looking to figure out which vessel has gone the longest without a media changeout, you could do that here. Now we drill down into specific treatment facilities for a deeper dive into the data. Here I've selected treatment facility A8. Again, that's an anonymized name. but we can see what the last measured PFAS concentrations are at each stage in the process for each PFAS analyte. So we begin with the black bar on the left, which is influent going into the treatment facility. Then if we look to that right, we can see the concentration in the lead and lag for each treatment train. As you'd expect, there's only initial PFAS breakthrough in the lead vessels of each train. Once it reaches a particular breakthrough threshold, we know it's time to change out the media. So this particular treatment facility is a 10-train system. And finally, on the far right, we have the combined effluent from all the treatment trains blended together and the finished product coming out of each treatment plant. And again, as you'd expect, it's non-detect for all of our analytes of interest. And still looking at treatment facility A8, we can move on to the time series data. So as opposed to the last tab, which just showed the latest PFAS values, the time series page shows us how PFAS concentrations have evolved over time at this given site. We can select which vessels we want to look at and the time period and get a detailed look at how PFAS is broken through over time. Naturally, you can also hit the little menu in the top right of each chart to download it as an image if you want to put it into a report or presentation. And here I'm showing the influence with that black line and also the lead vessels from the first 4 trains. And you can see how it's broken through over the last year at this site. And finally, the last page I'm going to show you is just the raw data tab. So this is just all the data we have for this selected treatment facility in tabular format. So one thing to note is this dashboard isn't and wasn't really meant to be a complete replacement for all the PFAS related workflows that we do. So there's still a lot of downstream analysis that we're doing or can be done outside of the dashboard. But this at least gives you a quick way to download that data without having to query your database. So even if you're not really using the dashboard for analysis and visualization, it can still save you time in that department. And that's it for the preview of the dashboard. So the question is, where are we taking it next? Well, for starters, we want to incorporate modeling and prediction. This one's been on our wish list for a while, but right now the dashboard is more descriptive than predictive, but we're hoping to change that. The advantage of all this data we're generating is that we're slowly building one of the largest and most robust PFAS breakthrough data sets out there. We're exploring several different options for prediction, from mechanistic models to machine learning. We want to not only be able to predict breakthrough PFAS given the first few PFAS measurements, but also be able to predict breakthrough for brand new sites based solely on their groundwater characteristics. With these forecasts, we can also better anticipate media changeouts, which has the added advantage of allowing us to bulk purchase media, which gives us better pricing. Next, we also want to expand access and partner data. Like I said before, it's the cities and retail agencies themselves that are the ones actually operating these plants, while OCWD provides PFAS monitoring and advises on when to change the media. So it's not a guarantee, but we're at least exploring the idea of possibly granting agencies direct access and turning this tool from an internal dashboard to a shared planning tool. And tying into that, we're also want to collaborate with them more to get more operational data from them, which will allow us to sharpen our breakthrough predictions. Last on the wish list is to integrate inorganic and water quality data. So we're already measuring several secondary water quality parameters, and we know many of these parameters interfere with PFAS absorption. There's things like total organic carbon and cations like iron and manganese, like Ryan mentioned. So this data can help us better understand why some groundwater profiles have faster PFAS breakthrough. And in summary, our goal is just to move from just tracking PFAS to actually anticipating PFAS, which can have a big impact on improving reliability and cost effectiveness at these treatment facilities. And thanks everyone for joining Ryan and I. We're about to do Q&A, but if you prefer, you can email us. Our addresses are listed on the screen. Thank you.
Thank you so much, Andrew and Ryan. Really appreciate the great presentation today. I'd love to invite our speakers, Andrew and Ryan, back onto the screen as we dive into some Q&A. And again, we're going to do our best to get to as many questions. We do have 15 minutes left in the hour, so we'll do our best to get to as many questions as we can live today. However, if we can't get to your question live, we're happy to email you a response after. So please do note your email address or your name, your account association with your question. We'll be sure to get in touch with you after. But with that, again, I just want to thank you both for your great presentations, and we'll dive into some questions at this time. Ryan, I want to kick it off with you. We had some questions from when you were initially talking about your vendor selection
Great.
in the PFAS program.
Mhm.
And the question was, what vendors were selected initially?
Yeah, the initial vendors were Evoqua, now Xylem, and Aqueous Vets. So
And then a question regarding the testing on the Evoqua resin. Were there any others you tested, and did you notice any significant performance differences?
and again, the media itself is Evoqua is the vendor selling it. It's actually Pure Light or not. Gosh, I keep saying Pure Light. It's not Pure Light. Um, Pure Light was one of the others that we tested. We do have others, and for some reason, I'm not remembering those at the moment. However, the report is available at, is it pfas.ocwd.com?
Yes.
Yeah, and anybody here is welcome to go. That's our public webpage. There's a lot of great information about the full piloting, all of the media tested, all of the results, and really it would do a much better job of explaining it than I would kind of off the top of my head at this point. So I definitely welcome you to look at Jacob's report on pfas.ocwd.com.
Thank you, Ryan. And then a question about this was asked during Andrew's presentation, but either Ryan or Andrew, what kind of field or lab equipment is being used to identify the PFAS? And if you'd like, we can punt that over to our lab team after the webinar if you're
Sure, I can answer that. That's
okay.
just
Thanks, Andrew.
tested using LCMS, using EPA method 533. The alternative is also EPA method 537.1, and they have a lot of overlap in analytes, but they're slightly different methods.
Perfect. Thank you, Andrew. And I believe you touched on this during your presentation about the dashboard, but can you remind us, is your dashboard code open source?
Well, the tools I'm using, yes, are open source, but the dashboard itself is not.
Thank you for that clarification. Regarding the data collection and management, Andrew and your team, how do you coordinate that with retail agencies and compare performance for any operational change recommendations that the team has?
Well, I mean, I think Ryan might be better suited to answer that one, but at least right now, we're mostly just serving as an advisory capacity to them. So we're not actually exchanging too much operational data right now. We're just mostly handling the monitoring of the PFAS coming out of the treatment vessels.
Yeah, and the dashboard is a great tool, and we're in kind of an interesting position here, having just started this whole PFAS treatment process a few years ago. We're barely getting to the first changeouts of our first vessels that we built. So there's a lot of data that we're still looking to capture before the dashboard or really any kind of tool would be good for projecting into the future. But ultimately, the goal is to, be able to use this to budget change outs, what kind of rate increases do the retailers need? Um, and then share this with the retailers, down the road again. And it may not be just that they can access it themselves, but at least we would have that data easily available to give to them upon request.
Thank you both. Um, have you ever seen a situation where the IX resin has broken through and contaminated the system's effluent water quality?
Not yet, knock on wood. We've been very fortunate so far, and These systems, the way they're designed, there's about a 4 foot deep bed of media in each vessel. So that's what gives it its 2 minute empty bed contact time. So we haven't really seen any channeling where anything has come through, and the strainers that are placed on the outlet of these vessels, are able to strain out this small, very small media. And again, fortunately, none of those have been damaged. And whenever we do media changeouts, those are inspected, and any potentially damaged screens are replaced at that time as well.
And Ryan, can you talk a little bit about how that spent media is managed? Landfill, reactivation, or incineration? And are PFAS just stored in California? Is the second question to that.
Yeah. Okay. So the first part, how is it handled? Well, the easy answer is we let Evoqua Xylem, who furnishes the media, take care of that for us. But the longer answer is most of this media is actually shipped to Utah or Nebraska and incinerated. They have to incinerate it up at very high temperatures, usually above 1600, 1700 degrees, in order to break that fluorine bond and ultimately destroy the PFAS that is attached to that media. Uh, then once that PFAS is destroyed, the rest of the media, which doesn't completely disintegrate, if you will, it just becomes big gel balls. That stuff is land disposed, just because the PFAS is gone at that point. There have been some issues we've had with media that could not be incinerated, and that has been land disposed in California at various certified disposal sites. But that is the exception, not the rule, so to speak. Uh, Granular activated carbon is really the only one that could be regenerated. But again, in that regeneration process, you're going to burn it at a high temperature, which is going to degrade some portion of that carbon. So it is possible to reuse it, but they would have to supplement that with brand new carbon to send it back and maintain that equivalent volume that was sent to them in the first place.
Thank you, Ryan. I'm going to punt these next few over to Andrew regarding the dashboard. How long did it take to develop the current dashboard? And how many data scientists are managing or maintaining the dashboard?
Well, that's difficult to answer because we sort of iterated over it over the years. I mean, maybe the initial dashboard took a couple months to build, but really it's an iterative process where we have to work with several different departments to bounce back and forth to actually figure out what people really wanted to see, features, stuff like that. And as for how many other data scientists are at OCWD, I'm the single one at OCWD. And yeah, I maintain the dashboard.
Andrew's holding down the fort. Is that related to the information that's available on the PFAS data? Andrew, can you talk a little bit about who owns the data, who maintains ownership of the dashboard, and where else it's available?
Yeah, sure. I mean, it's a joint collaboration, really between multiple departments at OCWD. So, I mean, we got help from our IS, our information systems team, who are actually maintaining the databases where the laboratory information sits, and they're able to sort of collate a lot of that data into specific views within the database. But then as for the visualization and aspects of it, that's punted over to us who are maintaining the dashboard. And then it lives on the OCWD's internal servers, which are again maintained by our IS team.
Thank you, Andrew. Is OCWD looking at short and ultra short chain PFAS in evaluating resin performance, or is the focus primarily on the MCLs?
Operationally, the MCLs are what we're looking at. However, R&D is continuing piloting. We're always piloting media for, what's coming next. in terms of new media that's more cost effective, longer life cycles. Um, but I'm just getting a message from our director of R&D that yes, we are. We are in fact, looking at those from a piloting perspective to make sure that we are in front of the curve, so to speak, with what could come up later.
Great, thank you for that. And how often, Ryan, can you speak to this? How often are you changing out the media?
That is highly variable, and the reason for that is that the media lasts a certain number of bed lives or bed volumes, we call it. So depending on the flow rate through the media, it could be lasting longer or shorter, but in general, we are seeing 3.5 years of use out of a media vessel. That's been kind of the average, 3 to 3.5 years. And that's for the first vessel. So you're starting with two brand new vessels. The second change out, when the lag vessel now becomes the new lead vessel, there will be some deterioration prior to it becoming the lead. So we anticipate that time frame may shorten down to 2 to 2.5 years, recurring after that.
Thank you, Ryan. And I've got a couple questions for you going back to your overview of the PFAS program and
Mhm.
talking about the well restorations to date. What criteria are used to prioritize wells for restoration?
For instance, I showed a photo of that one large site where all of the wells were brought to one treatment facility. That was all of the producers' wells or the retailers' wells. So that was a very high priority project, and in fact, it was the second project, I believe, to go online. Um, but it really is. There's several criteria. One being percentage of the total wells available to the retailer that are impacted, because that any water that they replace that impacted water with is purchased from the state at a much higher price. So from OCWD's and the retailer's perspective, we want to get those wells up and running and have them as close to that 85% of their water from the ground as we can. So that's really the number one consideration. The next consideration is availability of real estate. If they have the space available and they're ready to go, we're ready to go. And then beyond that, there's other little challenges and how bad the PFAS levels are compared to the MCL and can they blend and other things like that.
You know a general equipment cost for a 16 GPM system, or what does a media change out cost approximately, if you happen to know that, Ryan?
A media changeout per vessel is going to be, order of magnitude. Um, it's going to be in the range of $200,000 per vessel. And that's again, that's just a rough order of magnitude. The system itself, to purchase a system, which would be the two vessels, currently is about $500,000 for one of the 1220 systems, 1,600 gallons per minute capacity. So the 200,000 plus 200,000 plus 500,000, you're looking at close to $1 million, give or take, per system, just to have them installed and filled with media.
Thank you, Ryan. And I know we're at the top of the hour. We just hit 1 o'clock. I'm going to ask Ryan one more question, and we'll close out here in another minute. But you talked a lot about our phase one PFAS program and what we've accomplished thus far. What do you see as the biggest kind of remaining hurdles to restoring the remaining wells, or what's coming up for us?
The uh, one thing, the biggest struggle has just been procurement. Overall, COVID really hit us bad. There were supply chain issues really hit us bad. And some of those have gotten better. Some of them have kind of stayed, where they were with that. Um, So as more and more agencies are having to react and meet the MCL, I think some of the procurement issues and the time frames and lead times for these materials are going to continue to grow because, necessity and demand is going up and the number of manufacturers may not. So that's going to be the biggest hurdle, I think, going forward and finishing these up is just the schedule and the time that it takes to have these materials delivered for installation.
Thank you, Ryan. And I'm going to go ahead and close this out now, Ryan and Andrew. I really want to thank you for your great presentations, and I want to thank everyone that attended today. We do have a couple of questions that I know we will be following up with you on. So please stay tuned from the OCWD team, and we'll make sure we get any follow-up or written answers back over to you. So thank you again to everyone for joining us today. We hope you enjoyed it. And a friendly reminder that the presentation is recorded and will be available on OCWD's YouTube channel. The slides will also be made available on the OCWD website as well. So thank you. Have a great day and happy holidays, everyone. See you next year.
Great. Thank you.
Bye.